All right, so last time we said that we can use Newton's laws or classical physics and ideas about potential and kinetic energy to describe the behavior of two particles that are interacting. So let's review that with this example right here. Let's say you have two protons. We say if we were to calculate the potential energy between them, it will be represented by this red curve right here. Okay? And so we said, let's say that they are separated by this distance right here. Okay, so let's see, that's around 80 picometers on this graph. Okay, so the potential energy between them is given by this value right here. So that's the potential energy. Now let's see what happens. Let's say I were to hold them together at that distance and then release. Okay, so at that point they don't have any kinetic energy. The total energy is equal to the potential energy. So I'm going to draw a curve here, a horizontal line, to represent the fact that as they move away or towards each other, their total energy is going to remain the same. So this is their total energy. Okay, so what happens? What would actually happen is two protons will repel each other. So they're going to move away from each other. So they're going to move, so we're going to be moving to the right here to increasing distance. And so let's say they have separated further away. So their distance is further away. So let's say they're separated by this much, this distance right here. Well, the potential energy, as you can see, going from the original position to the new position has dropped. And so this difference right here between the potential and its total energy is your kinetic energy. So you can see as they separate, potential energy is dropping, potential kinetic energy is increasing. So they're going to be speeding up. So potential energy keeps dropping as they move away from each other because they repel. Kinetic energy will keep increasing. So this difference between the total and potential energy will be increasing. That's your kinetic energy. Eventually, though, it's going to level off. Potential energy is going to level off. There's going to be minimal interaction between them, and your kinetic energy will also level off. Total energy at all times would be the same. Okay, so that's how the two protons will behave because of the repulsions between them. Okay, there's a force between them that will cause them to accelerate as they move away from each other. Now, what if you add two electrons to those two protons? So you got two protons and two electrons. Okay, I'm going to say you got an electron here and an electron here. But these two electrons are just going to be going around those two protons, right? And as we have mentioned last time, we cannot really use classical physics. We cannot use Newton's laws to describe the behavior of electrons. We have to realize, people have realized that Newton's laws does not really apply to electrons. Okay, and so we have to use a more complete theory, a more accurate theory that's called quantum theory, which we'll talk about later. But the net effect is, okay, it would appear, because of the presence of those two electrons, that the potential energy between those two protons is given by this curve right here, the blue curve. Okay, this curve right here we cannot predict from Newton's laws. That's something you have to calculate from quantum mechanics. All right, so let me just illustrate the net effect of that. So let me go to a simulation so you can visualize what the net effect of having that kind of potential energy between two nuclei. All right, so let's go to phet.colorado.edu. They have a simulation for atomic interaction. So if you go to that website and you click on Run Now, it will download the Java simulation for you. Okay, and I already have that loaded here, so this is what you'll see. All right. So let's say we want to look at the interaction between two argon atoms. So this right here is a potential energy curve for the interaction of two argon atoms. All right. So let's just say I'm going to let me just move these two atoms around. So you got these two atoms down here. Look at what happens to the forces. I'm going to show you the forces. when the potential energy, when their distance right now, okay, at their distance, the potential energy is given by this dot right here, this blue dot or green dot. Okay, you'll notice at the minimum value of the potential energy, there's a balance of attractive forces. Okay, so this yellow uh, arrows represent attractive forces, and you have this pink arrows which represent the repulsive forces. So you can see at that minimum at that distance where the potential energy is at a minimum, you have a balance between attractive and repulsive forces. What happens as I move one atom away from the other? What happens to the what happens there? Your attractive, oops, sorry. Okay, so when they're further away, okay, you'll notice in this case, okay, the potential energy is over here, right here. There, the attractive force is stronger than the repulsive force. Okay, if I move them further away, okay, the force between them gets very weak. It's okay. There's hardly any force of attraction between them. You don't see those arrows. As I move them closer together, what happens? They start to attract. Look at that yellow arrow starting to grow, starting to attract, and then they start to repel. Okay, once you hit the minimum in your potential energy curve, there's a balance between attractive and repulsive forces. And now if I try to move them even closer together, the repulsion starts to rise drastically. Okay, you're crowding all of these charged particles into a much smaller region. Okay, it's a much smaller area, so you have a strong repulsion now happening between them. So you see your potential energy is rising. Okay, the repulsion is going to start growing rapidly, and so they're going to slow down. Okay, and let's see, you have, so you can see the steep part of your potential energy curve. That's called a repulsive wall, because that indicates strong repulsions between the two particles. Now, let's say I was going to, let me turn off these forces now. Let's say I'm going to put these two right there, okay, at that distance. So at this particular distance, you'll notice, okay, I'm going to draw a horizontal line here. That's the total energy of the two atoms, okay? Now what happens if I let go? You should notice as they move away from each other, the potential is going to be dropping, so you would expect them to speed up, okay, until they reach this distance right here at the minimum of the potential energy curve. And then as they keep moving further away, they're going to start to slow down, and then eventually the kinetic energy is going to level off, and so will the potential energy for them never to see each other again. So here goes. Okay? Let me repeat that one time. Return the atom. I'm gonna, okay. So as I let go, they're gonna speed up, slow down, and then level off the separation. Okay? So now how can I make these two atoms get stuck? Somehow, when they are somewhere at this distance, if there was a third body, a third atom that comes along and removes energy from them as a result of collision, then it's possible, let's say that their total energy would drop to, let's say, this much, just this much right here. Okay? So let's say when they were about this distance, somewhere around this distance right here, a third atom comes along or another molecule comes along, collides with the pair, and so they lose energy. So now their total energy is just this much. So now what you'll see is if I let go, your two atoms are stuck. They can't move away from each other. Okay? So what you see there is the vibration of two argon atoms in a molecule. This is what we would call an AR2, a diatomic argon molecule. All right, so that's how covalent bonding is formed. Now, this bond between two argon molecules is actually very weak. You can see that all I really need to do is give them enough energy. To give them enough energy to separate, I have to give them this much energy, what I indicated here as epsilon. Okay? This is also known as the bond dissociation energy. So what's given here as epsilon, we also represent that sometimes by the symbol d sub e. That's the bond dissociation energy. we can say that these two particles are trapped in a potential well, okay? But if they gain energy at least equal to epsilon, we know that we'll be able to set them free from each other. So we can make them separate, or the word is dissociate. So that's why this D sub E symbol is it's called the dissociation energy, okay? Dissociation. So you need to provide them with at least that much energy, D sub E, shown here as epsilon, to get them to dissociate. So, like I said, if I were to give them enough energy, raise the total energy they have, so a third atom could collide with them so that their total energy is now, let's say, I'm going to raise the total energy to at least that much, okay? Now they'll be able to separate, okay? So that's how bonding is formed. Now, how deep is this potential energy curve for a pair of argon atoms? This is about 0.01 electron volts. Okay, and earlier in another in earlier part of this lesson, we say that at 300 Kelvin, a room temperature, the average kinetic energy due to translation, the average translational energy was about 0.03 electron volts. Okay, so that means the dissociation energy is way less than the average energy of atoms at room temperature. So if you have a pair of argon atoms who happen to get stuck together in a covalent bond at room temperature, it doesn't take long for them to break apart. One collision with another argon atom and they're gone. They'll be free to move apart. That's why argon, as we find argon in nature, it's just a collection of argon atoms. They're not paired up. They don't form molecules because they can't stay together too long. Okay, so you could say these are the unmarrying types. These are the ones who don't want to get stuck. The bond between them is very weak. You say the potential well is very deep, very shallow. Okay. Now, what happens if you have two oxygen atoms instead? Okay, so let me pick two oxygen atoms right here. You'll notice the potential well depth is much deeper. Okay, this is about 5 electron volts. Okay, so if it collides with an average molecule at room temperature, an average molecule can only give it 0.03, 0.04 electron volts. Okay, you can go from down here to just a little bit higher. You can't get those two oxygen atoms to separate. That's why the oxygen that you see that we have in the air we breathe are diatomic oxygen molecules, O2. That's why we represent it by the symbol O2, because once your oxygen atoms get stuck, they're trapped in a very deep potential well. It takes at least 5 electron volts to get them to separate. And the average energy that a third body could provide by collision with these two oxygen atoms in the molecule would just be around 0.03 electron volts. Right? So that's what happens when two atoms interact. Okay, now if the oxygen atoms were separated to begin with, here's a true or false question. If I have two oxygen atoms, okay, at this distance, very far away from each other, so two separate oxygen atoms, if they were to collide, what's going to happen to them? Will they form O2 molecules? Two oxygen atoms were to collide, will they get stuck and form an O2 molecule? Now, let's see what happens, okay? Let's look at what happens as they approach each other. The kinetic energy is going to be more or less constant as they approach. What happens as they get closer and closer? The kinetic energy starts growing. The potential energy starts dropping really fast, okay? So they're going to speed up. Eventually, what happens? They're going to reach this point right here where there's very strong repulsions. And they're going to stop. Kinetic energy is 0 at this point right here, so that would be their total energy is just potential. And then they're just going to separate again, okay? And so, in fact, let me show you. Once they hit that point right there, okay, I'm going to move these two atoms closer together. Okay, let's say they have that much energy. Oops. me just drag this one instead. Oops. I can't drag it. There. So that was too fast. So basically, once they get to this point right here, everything, all the energy is potential. As they're just gonna separate, move really fast, and then slow down, and then level off, never to see each other again. So two oxygen atoms, if they're separated to begin with, they're not gonna get stuck. The only way for them to get stuck is somehow, if when they're close together, a third body comes along and takes energy away from them, so that the two atoms get trapped in what we would call this potential well. Okay, so let's go back to the slides. So this is what happens to hydrogen, and the same thing with two hydrogen atoms. If they happen to get stuck, okay, this well for hydrogen is very deep, okay, and so if you zoom in on this section right here, this is this green level right here. That's the average kinetic energy of molecules at room temperature, and this is a very, very deep well. Collision between an H2 molecule and a third body at room temperature is not going to cause those two hydrogen atoms to separate. And that's why hydrogen, the element hydrogen as it exists under ordinary condition, consists of pairs of H2 molecules. All right. So that's the simulation that I just showed you. That's the link, phet.colorado.edu. So let's take a look at this. Consider the potential energy curve here shown for hydrogen in red. Okay, which of the two energy levels, the green one or the red one, would we expect the hydrogen atoms to be able to separate further from each other? So let's say A and B. Let's make that a clicker question. In which of these cases will the hydrogen atoms be able to move farther from each other? When the total energy is at level A, or when the total energy is level B? Very good, at level B. In fact, at level B, they're not going to get stuck. They're just going to separate. Okay, they won't have, they won't be, they won't be able to form a bond. Okay, so at level A, they're going to get stuck between this distance and that distance. So they'll be vibrating between this distance and that distance right here. Okay, so we say at level A, when the energy is just given by A, then we say they have a bond between them. They're trapped in a potential well. Okay, and so like I said earlier, the depth of your potential well is called the dissociation energy, or the bond dissociation energy. That's the epsilon that you saw in the simulation. It's usually represented by the letter D sub E. Okay, so atoms will separate if they gain an energy equal to D sub E from a third body. Okay, so when atoms are separated as a result, okay, and their relative kinetic energy remains the same, then their potential energy will increase. So let's say you have this much energy to begin with, and they gain an energy equal to dE. Okay? So when they're separated, the kinetic energy remains the same. The kinetic energy, this much kinetic energy is the same as this much kinetic energy to begin with. So what happens essentially is when two atoms in a bond dissociate, okay, by absorbing an amount of energy equal to D sub E, their kinetic energy remains the same, but their potential energy has increased. So bond dissociation, we say, leads to an increase in potential energy. So you are basically, what happens there is you're converting your translational energy of your third body, the atom that collided with the pair, it's converted into potential energy of the separated atoms. So energy of a third body becomes potential energy of this pair of atoms that got dissociated. Okay. Now, similarly, if you are to form a bond, if you want two atoms to get stuck, okay, then they have to lose energy to a third body. Now, if you have bonded atoms in a molecule, okay, like I said, when they're already in a molecule, that means that they're trapped in a very deep potential well. You're looking at dissociation energy of about 5 electron volts. That's around 10 to the negative 18 joules. Okay, but if you have atoms or two molecules that have a very weak attraction for each other, then they have a very shallow well, typically less than 0.05 electron volts. The average, like I said, the average energy of molecules at room temperature is around 0.03, 0.04 electron volts. So any collision with a third body would just cause them to split apart, okay, to separate, about 0.04 electron volts. So that would be enough to split two molecules apart, but not two bonded atoms. Right. And this is more of the same. This is just given the dissociation energy of two nitrogen atoms in an N2 molecule, 1.6 times 10 to the negative 18, and the average translational energy given in joules would be given by this formula, 3/2 times K times T. Okay, so you can do the calculations for this, and you'll find that if you want an average atom to cause a pair of nitrogen atoms to separate, you're going to be looking at a temperature of at least 77,000 Kelvin. Okay, so N2 nitrogen atoms, as they exist in nature, come in pairs. So they're called diatomic molecules. That's 80% of the air that you breathe are N2 molecules, diatomic nitrogen molecules. All right, so let's do a quick check. We got the concepts right. As two protons approach each other, their potential energy will increase, decrease, or remain the same. Answer? B? Okay. Potential energy versus distance between the atoms. As they approach, approach means going that way, so the potential energy will be increasing. As they approach each other, they're going to be repelling each other. So they're going to slow down. If they're slowing down, kinetic energy is going down, so potential energy will increase. Now, if you plot potential energy versus R, you can see it's decreasing. It's decreasing as they separate from each other. This one says approach. Okay? Remember that when they repel, if two things are repelling each other, okay, as they move closer, they're going to have to start to slow down. So you're looking at decreasing kinetic energy. If the kinetic energy is slowing down, it's going down, then that means the potential energy must be going up. Okay, formation of a bond between two atoms. That involves what? Conversion of potential to kinetic energy or kinetic energy into potential energy. Let me just remind you what the potential energy looks like between two atoms that are bonded. So this is potential energy, and this is distance on this axis right here. So is it A or B? Here's a hint. When they're forming a bond, are they going from big separation to little separation, or from little separation to big separation? Okay, 7 said A, 5 said B. All right. if they're forming a bond, okay, so that means they start off far apart, right? And then they get together. They're approaching each other. So if they're forming a bond, that means they're if you're going to trace the potential energy as they form a bond, the potential energy would be from very large distance over here to short distance. Remember, for them to form a bond, they have to be at these distances right here. So you're looking at a potential energy that is going down. Okay, so if you're losing potential energy, okay, so that potential energy is being lost, okay? So they're going to lose energy to a third body. So the answer is, it becomes kinetic energy of a third body. Okay, so they're losing this much potential energy. It's being given away to a third body. So in other words, if you have a bunch of atoms, so let's say you have a collection of oxygen atoms, okay, not just a pair, but a collection of oxygen atoms, you can form O2 molecules because there's a lot of third bodies that can take away the energy from pairs of oxygen atoms. And so you have what's called an exothermic process, because as they get together, okay, they give up energy to a third body, so you end up with the molecules being formed, or the atoms around the wall surrounding them would now have more kinetic energy, so the object gets hot. Okay, so bond formation, we say, is an exothermic process. Exothermic process, due to bond formation, we say, okay, exo means out, thermic means heat, okay? So when two atoms form a bond, okay, you're converting their potential energy into kinetic energy of a third body. Okay, and so the system gets hot. The collection of atoms and the immediate surroundings will get hot as a result of bond formation. All right. Question? Let's just skip this. Let's just skip this next question. Okay, and let's just move on to the concept of energy and temperature. Are there any questions at this time? All right. So let's talk about energy and temperature. Okay. Before we do that, let's clear out some terminologies to make sure we understand each other. Anytime we use the word system, okay, you'll hear me use the word system a lot. Anytime we use the word system, that refers to just about anything we're interested in. So most of the time, the system we're dealing with in chemistry would be a sample of matter. Okay. And then surroundings would be everything else around that system. So that's the rest of the universe. Okay. Thermal energy, the term thermal energy, okay, refers to the sum of the kinetic energies of atoms in a system. Okay, so it's an example of what we call an extensive or extrinsic property. It's directly proportional to the amount of sample. More atoms you have, the higher the thermal energy, because you have more kinetic energies to add, because you have to add up all the kinetic energies of the atoms of your system to get your thermal energy. Okay, so thermal energy is not heat. Thermal energy, when we say thermal energy, we actually mean kinetic energies of the atoms in your system. The more atoms you have under the same conditions, then the more thermal energy you have. Now, temperature is a measure of what we would sense as the hotness or coldness of an object. It's actually an indication or a measure of the average kinetic energy of the atoms. So what we're saying is that when something gets hotter, when its temperature goes up, what's happening there is that your atoms are just gaining kinetic energy. So there's an increase in the thermal energy of the system. But since it's an average, anytime you take an average, you have what's called an intensive or an intrinsic property. It's independent of the amount of the sample. Okay, it's independent of the number of atoms in your sample. Now, what we call heat is not the same as temperature. Heat is actually the amount of energy that's transferred, okay, when you put something hot in contact with something cold. So if this is hot and this is cold, what we're saying is the average kinetic energy of the atoms in the hot object is higher than the average kinetic energy of the atoms in the cold object. It doesn't mean it has more thermal energy. It simply means it has a higher temperature, the average kinetic energy. Okay? So let me just illustrate that with an animation to help you visualize it. Go back to phet.colorado.edu. So you get an let me see if I can find that. Okay, right here, animation. This is what happens when you heat a sample of matter. All right, let me just pick water here. So these are water molecules in a solid form. That's what you get. What happens when you heat your water is you're giving the atoms more kinetic energy. Okay. So now you have thermal energy. I'm sorry? Okay, so you have here, by heating your sample, okay, you're putting your sample in contact with the flame. Now this flame right here, this is just atoms with very high kinetic energy. This is very hot flame, right? That's just atoms or molecules with very high average kinetic energy. So the collisions between the atoms here and the atoms in the container eventually gets transmitted to becomes collisions with the water molecules inside, and so your water molecules gain kinetic energy as a result of collisions. So by your molecules colliding with the walls, okay, and the walls colliding with the molecules of the flame, heat is basically a transfer of energy. It's a redistribution of thermal energy. Okay, it's a redistribution of kinetic energies of atoms and molecules. So if I were to cool this thing down, okay, what's happening now is the transfer of energy goes the other way. Your molecules are going to start to slow down. Let me hold this down. So I'm cooling my water. So now what I have here in my outside, that's low kinetic energies. Okay. You have atoms with low kinetic energies. And so as they keep colliding with the atoms in the wall and the atoms inside, eventually the kinetic energy from the atoms and molecules inside get transferred out, so the atoms inside lose kinetic energy. So the thermal energy inside drops. Okay? So the energy that's transferred is called heat. Okay? The energy that the atoms have just because they're moving, the total of that is called the thermal energy of the atoms and the molecules. Okay, so the hotter the object, the higher the thermal energy. The colder the object, the lower the thermal energy. All right. So heat is energy that's transferred when you're putting two things at different temperatures. So let's have a quick example here. Let's say you have 5 grams of copper at 50 degrees. 10 grams of copper also at 50 degrees. Well, Celsius. We have the same temperature, so what does that tell you about the average kinetic energy? Same temperature, same average. So neither. The answer to this question is neither. Which sample has higher average kinetic energy? Neither one, because they both have the same temperature. But which sample has more thermal energy? To Okay, so is it A or B? Which one has more thermal energy? Let's do a clicker on this one. A or B? Everybody said B. Very good. Okay, because it's like saying, let's just say, it's like saying you have 5 people versus 10 people. If the average, let's say, each of the average is, let's say, $10 per person. Okay, if you multiply that by 5 people, you get less money as opposed to if you multiply that by 10 people. Okay, so we say temperature, the average kinetic energy is an indication of the temperature is an indication of the average kinetic energy. It doesn't depend on how much you have, right? So that's an intensive property. So temperature, we say, temperature is intensive. An intensive property of the system. It doesn't depend on how much you have, how many atoms you have. You double the amount of sample of matter you have, you still have the same temperature. But thermal energy, on the other hand, okay, that's an example of an extensive or an extrinsic property. You double the amount of sample you have, then you're going to have twice as much thermal energy, even though the sample is at the same temperature. Okay. So here's another question. It's the same one. Okay, looks like I duplicated my slide. Oh no, I did not. This is at 100 degrees. Okay, 50 degrees versus 100 degrees. So which sample, let's look at our first question, has higher average kinetic energy? A or B? Okay, the higher temperature would mean a higher average kinetic energy. Which sample has more thermal energy, A or B? Still B, because you're looking at the same amount of samples, so the one with the higher average is going to have the higher total. It's like saying 5 kids with an average of $10 apiece versus 5 kids with an average, let's say 5 people with an average of $50 apiece versus 5 people with an average of $100 apiece. The, the group that has higher average would have a higher total. Okay, which way will heat flow? Will heat flow between samples A and B? Yes or no? Yes, good. Heat flows whenever the temperatures are different. Okay, and going back to the earlier question right here, in this case, if they're both at 50 degrees, even though you have 5 grams of one and 10 grams of the other, you have more thermal energy here. Since they're both at 50 degrees, they have the same average kinetic energy. There will be no heat flow. Okay, so heat flow is energy that's transferred when you put two things that have different thermal energies, different average kinetic energies, different temperatures. All right, heat and work. Transfer of energy can be classified as either heat or work, and we've already seen what work was earlier. We said it's the application of force over a distance, and as a result of that, you transfer energy. We talked about the work energy theorem, for example. We said that the work would be manifested as a change in the kinetic energy. Now, like I said, transfer of energy can be classified as either heat transfer or transfer by work. Okay, Anytime energy is transferred as a result of a temperature difference, if you're putting something hot next to something cold and energy is transferred, that's heat. Everything else, any other way of transferring energy is classified as work. At the atomic level, you can make the distinction between the two, by saying that heat is due to random collisions of atoms. So atoms are always moving, they're always colliding with each other. So as a result of these collisions, okay, kinetic energy gets redistributed from atom to atom, and so that's what happens when energy is transferred by heat. Okay, so it's just something that results because of random collisions of atoms. Work, on the other hand, is a more organized way of transferring energy. So if there's some kind of concerted motion or synchronized motion or organized motion of atoms that leads to collisions which lead to energy transfer, then you call that work. So for example, if you're going to squeeze a sample of gas, for example, you push on it, you squeeze it, you're doing what's work on it. If you're lifting an object, okay, there's a synchronized motion of the atoms, okay, a concerted motion of the atoms that causes the object to get lifted. That's an example of what we call mechanical work. Okay. Now, if you have an electrical wire, you have a copper wire, for example. Okay, you push electrons through that wire. That's what electricity is. Okay, you have a concerted or organized motion of electrons through the wire. That is what we would call electrical work. You're going to be transferring energy there because your electrons are going to be colliding with the atoms in your wire. Your wire is going to get hot. So let's look at an example here. Here's a clicker question. Which of the following ways of increasing the temperature of a nail is classified as heating? Putting it on a hot stove. Okay, your nail gets hot, right? I hit my nail with a hammer, it gets hot. I pass electricity through my nail, it gets hot. But which one of these is classified as heating? A, B, or C? Okay, the correct answer is A. Because heating, okay, means you're causing energy to transfer by putting two things that are at different temperature. So the stove is hot. Your stove is hot, and then your nail is cold. So two different temperatures. The heating of the nail in that case is called heating. Now, if you hit a nail by a hammer, okay, this top right here gets hot. That increase in temperature is not due to heating. The hammer is not hotter than the nail, okay? So that's what you would call mechanical work. And like I said, passing electricity through a wire, okay, you're increasing the temperature of the wire, but you're not heating it. You are doing electrical work on it. It gets hot, but you're not heating it, okay, in the precise definition of heat. All right. Now, when we calculate values for energy transfers, okay, when the system gains energy, we say that there's a net flow of energy, transfer of energy into the system. We assign delta E, okay, E, the final energy minus the initial energy, that's delta E. Okay, if you expect the final energy to be higher because energy went into the system, then E final minus E initial would have to be a number greater than 0. It would be a positive number. Okay? If delta E is negative, that means the final energy is less than the initial energy. So that's the delta E value is is negative if the system loses energy. Similarly, if heat flows into the system, we assign a value of 0, a positive value for Q. Q is our symbol for heat. and we say that the process is endothermic. Endo means going in, thermic means heat, so heat going in. If heat flows out of your system, then that means it's losing energy. Then so we assign a negative value for heat, and again, like I said, Q is our symbol for heat, and the process we say is exothermic. So here's an example. A hot piece of metal cools to room temperature. What's the algebraic sign of Q for the metal? Our system is the metal. Is it positive, A, or B, is it negative? B, negative. Good. Because if your metal cools down, okay, then that means energy must have gone out in the form of heat. Okay? Okay, where am I? Lost my place in the... All right. Let's talk now about heat capacity. Now, if there's no significant change in the potential energy of atoms when energy is transferred, okay, remember we said by transferring energy to atoms, we can make them really separate, okay, and so that could, or come together and get trapped in a potential well, and so we say that they can have a change. There's going to be a major change in potential energy. So if we're only dealing with just changes in kinetic energy, mostly kinetic energy, so no significant change in potential energy when energy is transferred, we can use the change in temperature to determine the amount of energy that's transferred. So the amount of energy that's transferred, due to heat, we represent that by the letter Q, would be directly proportional to the change in temperature. Okay? So we say Q is equal to some constant C times delta T. That's what we write when we say two things are directly proportional. In other words, I'm going to say that Q over delta T is a constant. Okay. What am I saying here? A bigger change in temperature means if these two ratios are to remain constant, then that means that implies a higher amount of heat that flowed into your system. A larger delta T would mean a larger Q. Okay, more heat flow, bigger temperature change. Okay, so that ratio of Q to delta T, that would be the energy, see the numerator is energy, needed to cause a temperature change of 1 degree Celsius or 1 Kelvin. So that's a definition of what we call heat capacity. It's the energy that's needed to raise the temperature of a system by 1 degree Celsius of 1 Kelvin. What should be the unit for C? Well, what's the unit for Q? Energy, the unit for energy is joules, and the unit for temperature change is degrees Celsius. So the unit for C is joule per degree Celsius or joules per Kelvin. Okay? Or you can write it as joules Kelvin to the negative 1. Joules times Kelvin to the negative 1. Joules times Kelvin to the negative 1. Joules per Kelvin or joules per degree Celsius or joules per degree reciprocal degree Celsius. Okay? Or in some cases, you write, instead of degrees Celsius, you write Celsius degrees because we're actually talking about temperature changes here. Now, I have a note down here that says if there is a significant change in potential energy, okay, then that means there's a significant change in the distances between the atoms. What you could have there could be a phase, what's called a phase change, or a chemical change, like changing from a solid to a liquid or a gas. That's called a phase change. Or a chemical change where you can have bonds getting broken and new bonds getting formed. We'll talk more about that later this semester. Okay. So for now, we're just talking about heat flow and temperature changes, how they're related when no other change is happening besides that. Now, for homogeneous systems, okay, that means it has uniform properties throughout. Okay, everywhere you look, any sample of the system would look just like the others, would have the same properties. We can calculate C by looking up the specific heat capacity or heat specific heat. Okay? Anytime you have the word specific in front of a quantity, that means per gram. So when you say specific heat capacity, that means heat capacity per gram. If you say specific volume, that means volume per gram. So generally, when you look things that you can look up are intensive properties. They shouldn't depend on the amount because you cannot list a number for every possible amount. So properties of matter are usually listed as intensive properties per unit mass. So in this case, per gram. So if you have specific heat or heat capacity per gram, if you want to know the heat capacity, all you have to do is multiply the value per gram by the actual mass in grams. So here's an example. Heat capacity, specific heat or specific heat capacity of water is 4.18 joules per Kelvin per gram. Look at this unit right here. It's joules per Kelvin. That's the unit for heat capacity. And then per gram would be the unit for specific heat. So what's the specific heat? What's the heat capacity of 100 grams of water? You're just going to say it's just going to be whatever the mass of the water is times the heat capacity per gram or the specific heat. So our mass is 100 grams. And our specific heat is given as 4.18 joules per Kelvin per gram. And if you did that, what do you get? 100 times 4.18 is 418. Now this has 4 sig figs, and I'm only showing 3 sig figs here, so I should only have 3 sig figs here. And gram cancels out. Grams times reciprocal grams would cancel out. So the final unit here for specific heat would be joules per Kelvin. Or you can also say this is 418 joules per degree Celsius. Okay, you don't worry about 273 here in the conversion between Celsius and Kelvin, because remember, in our definition of heat capacity, we're talking about temperature changes, not temperature readings. So 418 joules per Kelvin is the same thing as 418 joules per degree Celsius. All right, here's another example. How much energy is transferred when 100 grams of water at room temperature is cooled to 15 degrees? So you use the formula Q equals C delta T. Right? You say the amount of heat flow is directly proportional to the temperature change, and that direct proportionality constant is called the heat capacity. So what do we know here? What's our delta T? Oops, sorry. Our delta T is 10. Okay, actually it's your final temperature is 15 degrees Celsius. Our initial temperature is 15.0 degrees Celsius minus 25 degrees Celsius, 25.0 degrees Celsius. So our delta T is actually negative 10.0 degrees Celsius. All right, now that's our delta T. Temperature went down from 25 to 15. What is our specific heat? What's our heat capacity? 100 grams of water. We figured that out earlier in an earlier slide. The heat capacity we figured was 418, right? Mass times specific heat is 418. So 418 joules per Kelvin. So heat capacity is 418 joules per degree Celsius or per Kelvin, either one. So degrees Celsius will cancel out. Okay, so let me rewrite that here. 418 joules per degree Celsius. So a degree Celsius cancels out. So 418 times negative 10 would be 4,180 with 3 sig figs, and that would be the answer in joules. And this is negative. Okay, so the answer is negative 4180. So The actual amount of energy transferred is 4180. The negative here simply means what? That means heat flow out of your system, right? So the actual amount of energy transferred is 4180. But when we write the value for Q, we put a negative sign in front of it to indicate that we're dealing with heat flow going out of your system losing energy. Right. Now, an alternative formula you can use here, if you know the specific heat, is to say this is mass times the specific heat times delta T. Okay, so make a distinction between big C and little c here. Big C is the heat capacity, little c is specific heat. Now, depending on what textbook or who you're talking to, you might see specific heat written as S or C sub S. Okay, so all of these, little c, small s, or C sub S, are sometimes used as symbol for specific heat capacity. So how do you determine heat capacity? What you do in the lab, okay, and this is going to be your next lab after the graphing lab, is to use what's called a calorimeter. A calorimeter is an insulated container. So it's insulated, that means it's not going to let heat flow into or out of your system. Okay? And the way you create an insulated container is you can have like in your thermos bottle, you have a two-walled container there. There's a vacuum in between. A vacuum simply means there's hardly anything there, not even air. So remember we said heat flow happens as a result of random collisions. Well, if you don't have any atoms to collide with in between here, then you cannot let heat flow either in or out. So a thermos bottle keeps things cold, keeps things hot. Okay, the temperature inside remains more or less constant. Now, it's not a perfect insulator. Question? All right. Okay, so that's what an insulated container is, and the one you'll be using in your lab will be a styrofoam cup. Okay, and what you see in the walls of a styrofoam cup are that styrofoam has a lot of air bubbles in it. So in air, your molecules, your atoms on average are much farther away from each other. Okay, so the transfer of heat, okay, we said is due to collisions between molecules and atoms. So collisions are less frequent in a gas molecule than in a pure solid where you have all the atoms right next to each other. Okay, so that's why a styrofoam cup, you can see it's very light because it's filled with a lot of air pockets. It's a very good insulator. All right, anyway, going back to how to determine the heat capacity. What you do is you mix two samples that are at different temperatures in a calorimeter. Okay? So the heat lost by one sample must equal to the heat gained by the other sample. So if one sample loses heat, Q for the hot sample, for example, is going to be negative. And Q for the cold sample is going to be a positive number, right? So when you add Q hot plus Q cold, you should get 0 because no heat goes in or out of your system, out of your calorimeter. So if you call sample 1, our sample 1 and sample 2, that means heat capacity of sample 1 times delta T for sample 1. That's Q for sample 1. You add that to Q for sample 2, which is heat capacity of sample 2 times delta T for sample 2. Those two should add up to 0. So that's the most important equation to know as far as determining heat capacities are concerned in a calorimeter. So what you do is you mix two things. You can like mix hot water and cold water. Okay? So you can have cold water and then you pour hot water into it and then you mix. Okay, you know the temperature of the cold and hot water before. You measure the temperature after they mixed. So if you know delta T1 and you can measure delta T1 and delta T2. If you know one of the heat capacities, you can figure out the other. So the whole idea behind this measurement is you have to know one first. And so we have to define, that would be your reference, okay, your standard. Okay? So originally, Okay, before it was known that heat and work were just two different ways of transferring the same thing before joules work. Uh, the heat capacity was defined to be 1 calorie per gram per degree for water. Okay, so the calorie we now know in fact is equivalent to 4.184 joules. Okay, but before that, and that's why we have this odd looking number for water of 4.184, because originally it was defined to be 1 calorie, okay, as a reference for heat capacities. So water has a heat capacity of 1 calorie per gram per degree, or 4.184 joules per gram per degree. So water is a good thing to compare other things with. So you mix something with water. So I believe in that experiment that you're going to be doing, what we'll do is you'll have you have room temperature water, and you're going to put a piece of metal, okay, at least 200-gram piece of metal. This would be, or a piece of metallic rod or disc. You can, and then you're going to immerse that metal in an ice water bath. Okay, so your metal is going to be in an ice water bath. That's going to be at 0 degrees Celsius. So your water is going to be at room temperature, and your metal is you're gonna keep it in an ice water bath long enough so it will be at 0 degrees Celsius. You're gonna fish it out. Okay, so to make sure it doesn't get wet, you put it inside a Ziploc bag. Okay, fish it out, take it out of the Ziploc bag, and then drop it into your calorimeter in your styrofoam cup with the room temperature water, and you monitor the temperature. Okay. So you will know the heat capacity of the water. You will not know. You will determine the heat capacity of your metallic disc. Okay. So let's look at an example here. Let's say a piece of metal at 5 degrees is mixed with 100 grams of water at 25 degrees Celsius in a calorimeter. Okay. The final temperature. So your metal is cold. It's at 5 degrees Celsius. Your water is at room temperature. And so what happened to the final temperature? Let's say you found the final temperature to be 15. What's the heat capacity of the metal? So you'd say what? C of the metal. So let's call our metal number 1. Let's call water our number 1. Doesn't really matter. Sample 1 is water. Let's call sample 2 our metal. So you say C1 delta T1 plus C2 delta T2 equals 0. Okay, so what am I looking for here? Heat capacity of the metal. So I'm looking for C2. So I'm going to solve for C2. How do I solve for C2? Subtract C1 T1 from delta T1 from both sides. Yeah, gets rid of that. And then divide both sides by delta T2. That gets rid of delta T2. So our formula for C2 is just negative C1 delta T1 over delta T2. That's our heat capacity of the metal. So what's our C1? What's the heat capacity of 100 grams of water? We did that earlier. 100 times 4.18, right? So and that's 418 joules per degree Celsius. What's our delta T1 and what's our delta T2? Okay, our water, what happened to our water? It went from 25 to 15. So what's delta T for our water? And let's change that to 25.0 so we don't have a problem with sig figs. Negative 10, very good. So negative 10.0 degrees Celsius. Okay, that's negative. What's our delta T for sample number 2, our unknown metal? It went from 5.0 to 15.0. So from 5.0 degrees Celsius initial, the final temperature is 15. So delta T for our metal would be positive 10, right? So if we did that, uh, 418 times negative 10 divided by positive 10, and there's a negative over here in front. Negative of a negative is a positive number. So this whole thing is positive, okay? Your heat capacity should be a positive number. And in fact, the 10 and the 10 will just cancel out. So your answer is going to be positive 418 joules per degree Celsius. Okay, so that's how you determine the heat capacity of the unknown metal. Now, how would we know what the specific heat of the metal is? What additional information would you need? To get the specific heat of the metal is the heat capacity per gram. So specific heat would be heat capacity divided by the mass. So 418 joules per degree Celsius divided by the mass, which we are not given in this problem, so we cannot solve the specific heat. We know the heat capacity. We have the information to do the heat capacity, but we don't know the mass. But when you're doing this in the lab, you'll be measuring the mass of your metal, so you can get the specific heat of your metal. Okay? Note about the data analysis for this. What you'll be doing in the lab is you'll be monitoring the temperature of your water over like every 30 seconds, so temperature versus time. And then at the 5-minute mark, okay, at 5 minutes, you're going to put the metal in. So what do you think is going to happen to the temperature? The metal is colder than the water. Temperature is going to drop, right? And eventually it's going to level off. Now, because you don't have ideally your temperature should just level off straight horizontal there. But since you do not have a perfect insulator, what you'll see is you might see something like this. Okay? Your data might look something like that every 30 seconds. So what you have to do is this long-term trend right here, you have to draw the best fit line through that long-term trend and extrapolate to the time of mixing. And this temperature right here is going to be your final temperature. And then you wait 5 minutes before you mix because you want to also establish a trend in the temperature of your water before you added the metal. So you do a trend line through these data points. This temperature right here that you get is your initial temperature for the water. Okay? The final temperature for the metal and the water, since they're already mixed, would be this one. The initial temperature for the metal is going to be 0 degrees Celsius, since you're going to put it in an ice water bath. And so this difference is what you'll be recording as your delta T. So when you plot temperature versus time like this, you have what's called a thermogram. Okay? The word graph means writing, like telegram is writing from afar. Phonogram is writing with sound. Thermogram, this is a temperature versus time graph. Okay. Now you may note that you might say, why would the temperature dip below that trend line? The reason for that is because when you're mixing it, your thermometer might be right next to where the cold thing is. So it might end up being colder than what it should be. That's why you really need to establish that long-term trend so you can extrapolate properly to the time of mixing and get the correct value for the final temperature. Okay? All right, so let's do a few quick clicker questions here. If you pass electricity through a wire dipped in water, it will cause the temperature of both the wire and the water to increase. The temperature change in the wire is due to blank, and the temperature change in the water is due to blank. So what goes into these two blanks? Oops. Looks like I forgot to share my video feed. Huh? Okay. Pop. So you have electrons going through a wire. That's electrical work. Okay. So it's not A, it's not B. And so now by passing electrons through your wire now becomes hot, and the water around it is cold. So the transfer of energy between the wire and the water would be heat. Okay, so the answer is C. All right, here's another one. A pot of water at room temperature is placed on a hot stove. So your hot stove, and you have your water here. 5 kilojoules of heat is transferred. What's Q for the pot and what's Q for the stove? Most said C. Q for the water, so heat flows from the stove to the pot. So Q for the water is positive, and Q for the pot is negative. Very good. All right. Specific heat of a substance, if a 30-gram sample has a heat capacity of 3.00 joules per Kelvin, is how much? So what's the formula for specific heat? It's just the heat capacity per gram, so big C divided by the mass. So the answer is okay, let's see. Heat capacity is 3.00 joules per Kelvin. And the mass is 30.0 grams. So 3 divided by 30 is 0.100 joules per Kelvin per gram. Okay? Which is the same thing as 0.100 joules per degree Celsius per gram. The answer is A. Okay, this doesn't even have the right unit. It should be joules per Kelvin per gram. Okay, your units are switched here. You flip the two numbers. Okay, just remember that whenever you use Kelvin in these measurements, it's the same thing as Celsius. All right. And let's see, what's the specific heat of a substance if the temperature? Okay, let me see how many more questions do I have left. 4, 1, 2, 3, 4. Okay, let's go over this one. What's the specific heat if the temperature of a 35-gram sample increases from 25 to 27 with the absorption of 14 joules of heat? So what's the formula we have to use here? Q equals specific heat times delta T, or heat capacity, or mass times specific heat times delta T. What's our mass? 35.0 grams. What's our specific heat? Unknown. We don't know the specific heat. What's our delta T? 2.0 degrees Celsius. And what's our Q? Absorption of 14 joules, so that's positive 14.0 joules. How do we solve for our specific heat here? Specific heat is just equal to Q divided by, so it is divide both sides by mass times delta T, right? Delta T will cancel, mass will cancel. So Q over mass times delta T. So that's positive 14.0 joules divided by 35.0 grams times delta T, which is 2.0 degrees Celsius. So the answer is C. Okay, let's see. I pick up a calculator here. 14 divided by 35 divided by 2 is 0.2. Very good. Joule per Kelvin per degree. In fact, okay, you don't even need to calculate this, since this is a multiple choice question. If one of the answers is correct, then you know it can't be this. Wrong unit. This is wrong unit. Specific heat is joule per Kelvin per gram. This is the only thing that has the right unit. Okay? Okay, what happened to my slides? All right, how about this one? Okay, I think the rest of this is really just more application of the same questions relationship. Q equals MC delta T. So I think we should be done, right? We should be quitting now. It's 10 after. Sure, go ahead. Okay, let me just stop the recording.